Hi and welcome everyone. In this video, I want to go over the Newton's method. So let's see what Newton's method is and how it's used. First, then we can do some examples. So Newton's method, or sometimes we call it Newton-Raphson method, is used to solve equations which don't have specific formula or technique to be solved. These are more complicated equations like examples can be x times x plus 2 to the 50th power minus 1 plus x to the 50th power plus 5 equals to x. So these are kind of tough equations and no technique has been created to solve that. Well, of course, the Newton's method, or cosine x equals to x, or 1 over x equals to cube root of x minus 1, or sine x equals to x squared minus 2. Now, I know computers are calculators, they can solve those equations very fast. And it's good to know also that most calculators and computers and calculators are programmed the Newton's method to solve those equations and any equation. Sometimes there are some problems with the Newton's method, which we are going to go over that. But let's see how that works. Now, the first thing I want to introduce to you is the formula. So Newton's method works with iterations. So, and your goal is to find x, and x being the solution of an equation. And what you do, so x sub n plus 1 is x sub n minus f of x sub n divided by f prime of x sub n. To understand Newton's method, I chose to solve this equation. That's a quadratic simple equation, and you can use this by either factoring or quadratic formula. So there is a technique to solve this. So let's just solve this equation. So I chose factoring. When you solve this equation, you can take everything to one side. And of course, you can factor it. X squared minus 2x minus 3 can be written as x plus 1 times x minus 3. And you put that equal to 0. Then you can use the zero factor theorem. So take each factor and put it equal to 0. So you do get two solutions, x equals to -1 and x equals to -3. Now let's use the Newton's method for the same problem. And I chose to solve for x equals to 3 because you have to pick an x1 and then continue the iteration after that. So step number 1 is determining f of x. If you have an equation and you have two sides, to find f of x or to determine f of x, take everything to one side and 0 on the right side. So your f of x is the expression that's on the right side of the equation. So I put f of x is x squared minus 2x minus 3. Second step is find the derivative of that function. F prime of x is 2x minus 2. And you can guess a value for x1. We know our x1 is going to be 3 here, so I pick 2. And I'll show you what's the best way to pick a value. Now we're going to use the Newton's method. So Newton's method says x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. We have everything here, so let's substitute. I can say that equals to x sub n minus, this was our f of x, and this one was the derivative. So I just put x sub n for the x's. Now we picked x1 to be equal to 2. Let's find x2. x2 is x1 minus x1 squared minus 2x1 minus 3 over 2x1 minus 2. Basically, I'm using this formula. This is x2 and substitute all the n's by 1. Then it's a simple substitution. x1 is 2 minus f of x1 is f of 2 divided by f prime of x1, which is f prime of 2. And if you evaluate that expression, you get 3.5. Then we're going to go to x3. x3 is x2 minus f of x2 divided by f prime of x2. So basically it's x2 minus x2 squared minus 2x2 minus 3 divided by 2x2 minus 3, which is the derivative. And if you substitute x2 by its value, which was 3.5, then you get this number. And if you simplify that or evaluate it, you get 3.05. Just notice we are approaching to 3. x4, same way, is x3 minus f of x3 divided by f prime of x3. And if you substitute x by x3 right now, which is 3.05, and if you do again evaluate, then you get 3.0006, and that's very close to 3. Even if you go more, you end up getting a number that is very close to 3. So Newton method gave us the answer. How does that work? It's a good idea to see the proof of the Newton's method, the geometric representation. So let's see how this works. This is our curve or the graph of f of x. And as we know, our goal is to find when f of x equals to 0, that means the x-intercept of that graph. That point, the solution is the x-intercept. So now if I start, we pick an x1. So this point is x1 and f of x1. If I draw a tangent line at that point, so the equation of that tangent line is given by y equals to f of x1 plus f prime of x1 times x minus x1. So now what we want to do is take this line and then put it equal to 0. So do we find the equation and put it equal to 0? Geometrically, if I put that equal to 0, it cuts the x-axis, and I can call that number as x2. Now algebraically, if I want to take this and put it equal to 0, I can say that y is 0. So just solve this equation. 4x. So take that expression on the right side and put equal to 0. So basically find the x-intercept of the equation of that line, of the tangent line. And if you do the algebra, you can take f of x2, subtract f of x from both sides. So you get f prime times x, f prime of x1 times x minus 1 equals to negative f of x1. Then you can divide both sides by f prime of x1. And if you do that, you get x minus x1 equals to negative f of x1 divided by f prime of x1. Isolate x by adding x1 to both sides. So x will be x1 minus f of x1 over f prime of x1. We can call that x2 at that point. Then look at the graph now. If I go and hit f of x again, I can create another tangent line here. So now I can find that, I can say that point is x2 f of x2, and I can put the equation equals to 0. So the line is going to hit the x-axis, and I can call that x3. So the same way, now you don't have to solve it each time, you can just keep using the formula. So for x2, we said the value of x2 is x1 minus f of x1 divided by f prime of x1. Same way, once you find x2, then you can go and find x3, which is x2 minus f of x2 divided by f prime of x2, x4, and so on. Let's see what happens if we do that. So we have x3, we're approaching to our point. I'm gonna hit the curve where x3 is and then cross the x-axis and so on. So it gets to a point that you get once our xn or xn plus 1 is equal to the x-intercept, then you keep getting the same number, and that's when you know you're done, or very, very close to that number. So that's why the general formula for x is x sub n plus 1 is x sub n minus f of x sub n divided by f prime of x sub n. Now, it's good to know if r is the solution of f of x equals to 0, then we can say r, if r is the solution, is limit when n approaches to infinity of x sub n. So you keep the iteration until you get the same number. That's a way to present that. Now, as I said, Newton's method doesn't work all the time. Sometimes it fails. So graphically, it's very easy to see where it fails. So if I start with x1, case number 1 here, if I extend that tangent line to the x-axis, then if I go to x1, we notice that f prime of x2 is 0. So the denominator will be 0, so it's going to be undefined, so we can't continue our iterations. Or let's look at this case. We can start this graph. That's the graph of cube root of x, but then let's see what happens. I start with x1, so I go to the graph and I extend that to the y-axis. I cross the x-axis and we get x2. So if I come down to the curve, hit the curve and draw the tangent line, as we see, we get further and further from 0, which is our solution. So we can't get a solution this way. So we go even x2, I showed it to x4 gets further. So there are some cases that Newton method doesn't work when if you see the solution, if the graph is hard, and if you see the solution gets further and further and you don't get the same number, that means Newton method is failing. Now there's an example, that's a good example. If you want to solve the equation x cosine x equals to x, so this doesn't have a specific method. Let's see how Newton's method can help us to solve this. So first, take all the terms to the right side. So, or here you can take it to the right side. Yes, so that's not good. You can subtract cosine x from both sides. So you get x minus cosine x equals to 0, which is the same equation. So determining f of x is x minus cosine x. Right away, find the derivative of that function, which is 1 plus sine x. The problem is to choose an x1, and you want to be close to that. So to choose x1 in this case, I know I have two functions. One of them is x, and the other one is cosine x. So basically, the solution of this equation is where those two functions cross each other. So I graphed y equals to x, and we have this is the graph of cosine x, and we know we're gonna hit that. These functions, they cross each other at that point. So here is pi over 2, here is 1, so it's very close to 1. And again, it's just to pick a point, and the Newton's method is gonna take care of the rest. So the best point I could pick was x equals to 1, because it's very close to where those two functions intercept each other or cross each other. x1 equals to 1, write the formula for the Newton's method and substitute. So you know x sub n plus 1 is going to be x sub n minus cosine x. That's our function. And over the derivative 1 plus sine x sub n. First point was one, make sure you're in radian mode with your calculator. So substitute, and if you evaluate, you get 0.750363868. Then we can find x2, x3 by substituting x2. And if you do that, then you get 0.739 and so on, that number. So, and the rest, I just wrote the solutions here. If you calculate x4 by using the same formula and x3, then you get 0.7908. x5 will be 0.739085. So we see that x is a very close number to 0.739085. So if you start getting the same numbers, then you can like even 3 digits should be enough. If you get that, then you can stop right there, and that's going to be your x-intercept for that equation or the solution of that equation. It's a good idea to practice a couple of problems with the Newton's method. And again, the proof is very important. Know how, where the or where it's coming from. So watch this video a couple of times, and I'll see you in my next video. Have a good one, everyone.